All right, so hello everyone in the future watching this. I'm Everett. I'm back. I'm here with Evan,
Hello.
and we just finished our tutorial on Archimedean spirals, and so uh, now we want to get into equiangular spirals. So, Evan, I know you haven't designed a spiral antenna, but is there one you find maybe visually appealing?
I think all the Archimedean spirals and they, I guess they all look pretty appealing to me. They look like something out of the movie Saw.
Yeah, the Archimedeans you said.
Yeah, but I think they all look kind of cool. I wouldn't say there's one that looks cooler. I guess I don't know.
Okay. Well, when designing and constructing these antennas, especially in HFSS, I prefer equiangular spirals, and I want to show why. So I want to go into the remote server, the HFSS server again, and show the Archimedean spiral we designed. So let me just make this bigger by adding more turns. So the thing about Archimedean spirals is that they take a lot of data points to plot. So I want to show that. So I'll just zoom in here. So you can see right here, like the spot at these as the spiral gets bigger, we can see more of the angular shapes, right? And so that's just because we don't have enough points to get to the nice curves of the spiral. So if we want to do that, we have to go into our variables, our NP, our number of points, and we have to increase that. Let's double that to 1,000. All right. And so now we can see we're getting more of a curvature shape into our spiral. So the thing is that when we have more data points, it's going to take longer to simulate. So that's why I prefer equiangular spirals, because equiangular spirals actually don't need as many data points as Archimedean spirals to plot. So let's just get right into that. So we're going to start with Matlab. So just bear with me for a moment. All right, so here's a Matlab. Evan, can you see it?
Yes, yes,
Yeah.
I can see it.
Okay. Good. Good. So here's the work we did for Archimedean spirals, but now I'm just going to make another section, and this section is going to be on equiangular spirals. All right. So um, for equiangular spirals, well, the equation is that r, the magnitude, equals r naught, and then we're going to have e to the a, e to the a phi. So right here, if you can see that. So this is our equation for equiangular spirals. Lowercase r equals r naught times e to the a phi. Well, r naught is actually our initial distance from the center. For the Archimedean spirals, we actually had to add that in as b here. But for equiangular spirals, that's just a part of the equation is r naught. It's our initial distance. And then, of course, a here is our spiral factor. Again, the spiral factor is how fast the spiral grows outwards. So now that we have this, now we can make our or derive our parametric equations. So in Cartesian form, so we have x, of course, will equal r naught here, e to the a phi, then times cosine of phi. And then y equals the same thing, except it's going to be sine of phi. So this is going to be sine of phi here. So this is our equations for equiangular spirals. Well, now let's just get into plotting and see what we can do about that. So I'm just going to put my header here. This is just a good programming practice to have a header. All right, so let's define some variables. So, well, we have this initial distance. Well, let's just use B1 again. So we have B1, and let's just say that's 1 for now. And then we also want our spiral factor. Let's just call this A1. Let's just make this 0.1 for now. And then we also want to specify the number of turns we have. So we have turns. Let's just make this 2. All right, and now let's specify our independent variable, so t. So of course we want our TS1, our T start one. Let's just say that's just going to be 0. And then we also want our T end one. That's going to be 2 times pi times turns to implement the number of turns we want. Now let's make our full T array. So it's going to be T1 equals linspace. We start at TS1 and at TN1. And let's just put NP, number of points. And then let's just use 100 points and see where that takes us. All right, so now that we have that, let's get into making our parametric equations. So we'll say we'll have x1 equals b1 times the exponent e to the a1 times t1, then element by element matrix multiplication. This is going to be cosine of t1. And then we'll have y1 equals the same thing, except it's going to be sine of t1. All right, so now let's just make our figure and let's plot that. So that's going to be plot x1 by y1. Let's make that blue right now. Let's see how this looks. All right, so we are beginning to see our equiangular spiral. It doesn't look like too much right now. So let me put our limits here. Let me just copy paste this. All right, so now let's just plot the other spiral arm. So again, to do that, we just make an x2 equals negative x1, and then y2 equals negative y1. Now we hold on, we plot that x2, y2. Let's make that red. All right, so now we have our other spiral arm here. So things are looking good here, but these lines just represent the inner edge of the spiral arm. Of course, we want to make our outer edge also. Well, to do that, we need to specify another variable. Let's just say the initial width, W. So let's say our initial width is just 0.5 for now. And then let's say we also have a B2. So B2 is B1 plus our initial width. So this is going to be the initial distance of the outer edge of the spiral arms. So now we can make those. We can say x3 equals b2 times exponent, or e to the a1 times t1, then cosine of t1, then y3 equals the same thing, but the sine version. All right, so now let's plot that. So we'll do hold on, plot x3, y3, blue, and then we'll also get our other outer edge. So x4 equals negative x3, and then y4 equals negative y3. Let's plot those as well. We'll do hold on, plot x4, y4. This is red. And let's see how this looks. Okay, so it looks kind of crazy right now, but that's just because we have some overlap. So let's decrease our width here. Let's make this 0.25 right now. And now when we do that, we can see our spiral arms coming into play here. We can see we have an initial distance, we have our initial width, and we have our spiral arms just growing outwards here. And we can also see that we're only using 100 points right now, as opposed to our Archimedean spirals, which we used 500 points. So this is what I mean by equiangular spirals. They need you don't need that many points compared to Archimedean spirals. So that's why I like using equiangular spirals at this moment. All right, so we have that. Now we just need to get into making our bounds. So again, just like the Archimedean spirals, you can just either have it stop with a line here, or you can either have it taper to a point. So I'm going to show both of those. So I'll just copy paste this into a new section. All right, so first we're going to start with making our outer bounds with just a line here. So if we want to do that, we need to figure out the x and y coordinates of both of these points. Because remember, this doesn't have to be just an integer, the number of turns. It can also be something like a decimal, like 2.54 turns, something like that, where it could, the spiral ends at an angle here. If I can show that right here. So a little more zoomed out here, we can see that the spiral arms end at an angle instead. So if we want to get to those points, well, we have them. We have them right here. So let's just make our x5. x5 equals this, but we plug in TE1 this time. All right, and then y5 equals this, but we plug in our TE1 again. So now we have the x and y coordinate of this point here, where this spiral ends. We just need the x and y coordinate of this one. Well, this outer edge here, this ends right here. So we have x6 equals this, where we plug in TE1, and then y6 equals this, where we plug in TE1. All right, so let's plot that. Let's do hold on, plot, and then we're just gonna make our vector here directly. So it's gonna be x5, x6, then comma, y5, y6, and then this is gonna be the blue arm. So we plot that. Yeah, now we have a really nice outer bound for this spiral. So if we want to do that to the other side, well, let's just make these negative. So let's do, whoops, I'll paste that right there. So we'll make these negative. This will be negative. This will be negative. This will be red now. So now we have these really nice outer bounds where it's just a line stopping it. But that's not what I like to do. What I like to do is I like to make them taper, just like I showed in for the Archimedean spiral. So if we want to taper these arms, well, first we need to figure out where the outer edge stops. What magnitude is it as? Because what we're going to do is we're just like the Archimedean spiral, just like the Archimedean spiral, we're going to extend this inner edge here until it's at the same magnitude as the outer edge right here. So the outer edge has this magnitude here. We just need to plug in TE1. So doing the tapered outer bound now, we'll say that x5, or not x5, but the magnitude R1 is this magnitude here, but plug in TE1. All right, so now that we know the magnitude that the outer edge stops at, we need to figure out what value of phi does it take to extend this inner edge here all the way to R1. Well, if we go back to our equation of an equiangular spiral here, and if we were to solve for phi, so let me put this right here. If we were to solve for phi, we would get that phi equals, make a fraction, this will be equal the natural log of lowercase r over r naught over a. So where lowercase r is going to be r1 here, capital R naught, of course, is our initial distance, which for our inner edge is just b1. And then a, of course, is just our spiral factor. So we can solve for Tn2. Tn2, again, is just a natural log of R1 over B1 divided by A1. All right, so let's just put this up here. And now let's just make our new T vector. So T2 is Lin space. It starts at TS1, ends at Tn2, NP for number of points. And now for our inner edge arm, for the inner edge side of the arms, we'll replace it with T2. So we'll just do this, T2, T2 here, T2 here, and T2 here. So if we run it, you can see that the inner edge has now extended until it reaches R1. And so now, just like the Archimedean spirals, we'll just we'll make a piece of a circle, just a piece of a circle with radius R1 that extends from TE1 to TE2. So let's make a new T variable, or independent variable, T3. Lin space, it starts at TE1, then goes to TE2. Let's just use number of points here. So our x5 is going to be R1 times cosine of T3. Our y5 is going to be R1 times sine of T3. And now let's just plot that. X5, Y5, this is the blue side. And if we do that, we have our very nice tapered outer bound. All right, so let's just do that for the other side. For the other side, it's just going to be x6 equals negative x5, and then y6 equals negative y5. And then we can just plot that.
And so, Everett, could I ask you again, does it improve the antenna anyway by tapering it like that, or does it?
I believe so, because in most antenna design, you don't want like sudden sharp angles, or sharp angles just aren't preferable in antenna design. So I believe tapering is the way we want to go. Even Dr. Jackson, he thinks he prefers like tapered and designs and curves as opposed to any sharp angles.
Yeah, so you're just kind of trying to avoid having right angles.
Yeah. So
okay, cool.
We run this and we get our very nice tapered outer bounds.
Nice.
All right, so now that we have that, let's just make our inner bounds. Well, this is also easy. We know we can just directly plot it here. So we can just hold on, plot. So it's going to be B1 and B2. And then just a zero vector here. And then this is going to be the blue side. And then for the other inner bound, it's plot. Well, we can just copy paste this. The negative B1, B2 vector. And let's make this red. We run that. Now we have our very nice inner bounds here. And again, now this is pretty much all we need in Matlab. So again, this is a very robust design. So we can change B1, you can change A1, you can change the number of turns you need, or the initial width here. So if you wanted to make B1, like let's say 2, maybe the number of turns, something wild like 3.8934, and you were to run that, you see it's a very robust design. It holds together. And although we do need more points, more than 100, let's say let's try 300. All right, yeah, much better curvature here.
Wow, yeah. It's really cool.
Yeah, so this is our equiangular spiral. Oh, I think I put in too many turns here because equiangular spirals grow much faster than Archimedean spirals. So that's the deal with equiangular spirals. Yeah, there we go. All right, so now that we know how to plot it in Matlab, now we can just move everything over to HFSS. So I'm going to open my remote server here.